Good evening. So here is lecture 18, and in this lecture we're going to be covering the Fourier design of slice-selective excitation pulses. Right? These are pulses that select only a slice in space and nothing else. Right? So these are the kind of pulses that you would want to play out if you're just trying to excite and collect data from one two-dimensional slice. So last time what we talked about was we talked about the small tip angle approximation, which says that the slice profile, which is we define as the transverse magnetization as a function of space, is equal to the Fourier transform of an RF pulse B1 of t, which itself is a k-space weighting function. That is, B1 of t is a k-space weighting function in the small tip angle regime, if B1 of t only excites small tip angles. Okay, so this time we're going to apply this relationship to design slice-selective RF pulses. Okay? So, ideally, what we'd like to do in slice-selective excitation is we would like to get a slice profile with perfectly sharp edges, right? We'd like a slice profile that looks like a rect function, right? In that it's 0, 0, 0 here, and then all of a sudden it jumps up to be in slice, and then right away it drops down again once we move back out of the slice. Okay? So that would be then mathematically a rect function. So I don't want to use black here. Let me see. There we go. So that is the function rect of f. So here I'm working in frequency coordinates. It's just like normalized space here. Okay? Now the Fourier transform of that, of course, we've seen a couple times now in class, is a sinc function, right? The Fourier transform of a rect is a sinc. So then the Fourier transform is sinc of t. Okay? Now that's what we'd really like to do. Now unfortunately, as much as we would like to generate this slice profile, it just isn't practical, since the sinc function that we have to use for B1 of t continues indefinitely forward and backward in time, that is for positive and negative time. So one thing you can do is just truncate it, right? You just cut it off. So you truncate it. You just cut it off at a given negative time and a given positive time, right? And so then when you do that, you arrive at what is called the truncated sinc function. And that is this guy here. Okay, so then the width at which you are truncating it, you could call arbitrarily, you could call it 2n, right, since the function extends to minus n, from minus n to n. And here, what we effectively have done is multiplied the sinc function with a rect function, right? So a function that is 1 everywhere inside the times that we want, and 0 elsewhere, right? So truncating it is equivalent to multiplying our sinc function with a rect function. So then mathematically we can write this pulse as sinc of t times rect of t over 2n. Okay? And then the Fourier transform of that is going to be this guy right here. So because these two functions are multiplied in the time domain, they are going to be what? They are going to be convolved in the frequency domain. So then you're going to get rect of f convolved with sinc of 2 times capital N times f times 2 times n. Okay? So the rect is the Fourier transform of the sinc, and the sinc is the Fourier transform of the rect. Right? And so because they're multiplied in one domain, they're convolved in the other. Okay? So this is a fairly hideous slice profile. Right? And it turns out that this distance between the first time that the profile hits 0 and the last time it is at the desired value is about 1 over 2 times n, and this guy is called the transition band. Okay? So the width of the band that goes from the inside the slice profile to the stop band, to the point at which the profile is 0 for the first time, that is called the transition band. So the width of this guy is called the transition band. Everything outside that and outside the transition band is called the stop band, and the band in between is called the transition band. This is a common nomenclature from digital filter design. Okay, so why is this so terrible? Well, it has a lot of ripple, right? It just has way too much ripple. It's really big ripple. That's what this guy has. Okay, so the profile just has too much ripple to be really acceptable for use. And why does it have too much ripple? Well, the problem is the rect function that we truncated the sync with. The problem is the rect function we multiplied the pulse with to truncate it. So multiplying with this rect resulted in a convolution, as we saw, of the slice profile with a sync function, which itself has ripples, and then subsequently created huge ripples in the convolved profile. Okay? So the solution to this, the trade-off that we make then, is to use what is called a windowed sync function, and this is what you're going to implement on the homework. And so it looks a little bit like this. Essentially, you take a sync function and you multiply it by a window function that is no longer a rect, which would look like that, but is instead this shaped function, right? It looks a little bit like a Gaussian shape, right? And so we're going to call that guy W of t over 2 capital N, and that is equal to then the multiplication of a sync as a function of time times W of t over 2 times capital N. Okay? And a typical choice for this, and indeed what you're going to implement in the homework, is a Hamming window. You can use a number of different windows, but we are going to use a Hamming window, and that is a popular choice in practice for MR. Okay, so what do we pay for this, right? There's no free lunch. So this function, as you might guess, is multiplying our sync by this function, as you might guess, is going to reduce the rippling, but that's going to come at a cost, and the cost is that we're going to have an increased transition width. Right, and that's also not a great thing, but it's usually the trade-off we prefer to make. So now the transition width is going to be 1 over n, whereas before it was half that. It was 1 over 2n, if you recall. Right, so we've gotten a wider transition width for a lower ripple. And this is going to be a trade-off that's going to come up again later as we talk about SLR pulse design. So mathematically, this function is rect of f, that's the Fourier transform of, f, that's the Fourier transform of sync of t, convolved with 2 times cap n times w of 2 times cap n times f. Okay, that's the Fourier transform of w. Alright, so so this should be little w, and that is really a capital W, right? So I'll call this maybe tilde w, just so you can see it in my notation there. So it's the Fourier transform of the window function, which is not necessarily analytically the same thing as the function itself. Okay. So again, as I just said, we have reduced ripples, right? We have reduced ripples, but the cost that we pay for this is an increased transition width. Right? We doubled the transition width in order to reduce the rippling. Okay, and this turns out to usually be what we are going to prefer. And the reason for this is that in practice, when you're imaging, it is going to be better to maybe have a little bit of leakage of signal, right? We can consider the signal that would come into our slice from this larger transition region as being unwanted leakage of signal from nearby slices, right? So in practice, it's usually considered to be better to have leakage from slices that are directly adjacent to our slice than from slices that might be farther away from our slice, which would happen if we had big ripples from the sink profile that are far away, right? If you remember that when we do slice selective excitation, we're not going to, after that, do any Z encoding along this dimension, right? So our imaging system, our imaging readout is not going to resolve along this dimension. So everything that is excited along here is just going to alias into the slice. And it's better to have that aliasing happen from spatial locations that are right next to the slice than it is from locations that are far away. I hope that makes sense. So now we're in the position to define some pulse shape characteristics. And the main one that is of interest is going to be the time bandwidth product. So this is a unitless metric for all digital filters, including RF pulses, and it is equal to the product of the duration of the pulse, which is capital T, and the bandwidth, which is BW for a pulse, or really this holds for any digital filter. Okay. Now in our example that we just showed earlier, the time of the pulse was 2n, right? It went from minus n to plus n, and so the total duration of the pulse was 2 times n. And the bandwidth was just 1, right? So that means that then the time bandwidth product was equal to 2n. Okay? And this happens to be equal to the total number of 0 crossings in the pulse, and so that means that n must have been 2 before. Right? So a sync function, if you recall, is it's 1 at 0, and then it has 0 crossings at every integer. Okay? And indeed that's what we see in our pulse here. Okay, so some examples of different pulses with different time bandwidths and what it is that we use them for in MR is due here. Okay, so a simple time bandwidth 2 pulse that really looks like a gradient waveform is very commonly used for excitation pulses in SSFP sequences. That is, I don't expect most people to know what that means, but those are steady state free precession sequences. And alpha just means that it's an excitation that is not 90 degrees. Okay? So that is common to use a time bandwidth 2 pulse for that, just because we want a really, really short pulse for those kinds of sequences. Another type of pulse, another one that is commonly used is a time bandwidth 4 pulse for 180 degree excitations, and those are used for refocusing mostly. Okay? Another time bandwidth product that is common is a time bandwidth of 8, and those are used for 90 degree pulses and also for alphas, right? Alpha being an excitation pulse that is not 90 degrees. And the final one is time bandwidth equals 12, and these guys are used for slab for saturations, which are always 90 degree pulses, right? Those are actually pulses wherein we want to kill off the signal in a certain spatial location, and so we excite that signal with a 90 degree excitation, so that kills off the MZ component, right? Because when you perform a 90 degree excitation, the MZ component is 0 afterwards. Then if we play out a lot of gradients right after that, we kill off the signal from that excitation, and so that's called a saturation pulse, and we typically want sharp corners on those profiles. And the other thing we use them for is slab select alphas, right? Slab select pulses that excite something less than 90 degrees. Okay, and so the thing to note here again is, as I said, that the time bandwidth is equal to the total number of 0 crossings in the pulse. So you can see that there are 2 0 crossings in the time bandwidth 2 pulse, 1, 2, 3, 4 in the time bandwidth 4, 1, 2, 3, 4, 5, 6, 7, 8 in the time bandwidth 8, and again 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 in the time bandwidth 12. Alright, so everything checks out. So I will say one other thing is that this is really a GE view of the world. These are the different kinds of pulses that are really used on a GE scanner. But on a Phillips system, if you sit down and look at the pulse sequence of a Phillips system, you're actually going to see a little bit different pulse shape, which is going to look a little bit like just one up to just after the main lobe of this. So it'll be like all the negative time points in the pulse up to just after the main lobe, and then it's truncated at this point. And that's called a minimum phase excitation, and we'll talk a little bit about that later on in the class. Okay, so now let's see what happens as we change these parameters with respect to each other. So let's say that we fix the bandwidth of the pulse, but we make the duration, capital T, longer. Right? So then what happens to the time bandwidth product? Well, it will increase. Right? Time bandwidth increases. Okay? So then here is an example of this. So time bandwidth 1, 2, 3, 4, that's equal to 4. Right? And the Fourier transform of this will be a slice profile. There's the transition width, it's about 1 over n. Right? And then on the right hand side here we have increased the time bandwidth by making the time longer. Right, so pretty much the main lobe, so the main lobe and the two side lobes, first side lobes are going to look exactly the same. They should be exactly the same in amplitude and width. But now we've added more lobes onto it so that we get a time bandwidth of 8. And what this is going to do is give us a sharper, a narrower transition width. Right, it's actually going to cut the transition width in half to double the time bandwidth product. And so then, but at the same time, we're going to have the same excitation width, right? So we get the same excitation width, but a narrower half the transition width. And so what we have here is what we would call a more selective profile, right? So we're going to have less leakage here of signal from adjacent locations that are right next to the slice, right? We have here a better approximation of our ideal rectangular excitation profile. Now conversely, what happens if we fix the duration, which again is capital T, and we increase the bandwidth? Okay, so in the left-hand side we again have a time bandwidth of 4, and let's say that the amplitude of our pulse is 1/2. Right? Sorry, so if we fix the duration and we increase the bandwidth, then what will happen is if we double our bandwidth, then we will get double the amplitude, right? This is 2x amplitude. And so then time bandwidth we have doubled here, right? The number of zero crossings is now equal to 8. Right? That results in a doubling of the RF amplitude. Now what have we done here? Well, we're going to have the same transition width, but because we have doubled the bandwidth, we will now have twice the bandwidth, right? We'll have twice the width of our slice profile. Okay? And so what we have here is a wider slice profile. Okay, so and it might be a little counterintuitive, or not counterintuitive, but just unintuitive as to why the excitation pulse has to be bigger here. But if you think about it, if you think about the fact that the DC component of the Fourier transform of a signal is just the integral over all of that signal, right? Then the integral over this slice profile is one thing, right? It's actually equal to 1/2. It's the DC component of the pulse, while the integral of this slice profile is going to be twice as big, right? Because it has 2 times the width, so there's going to be 2 times the area underneath the slice profile, and so it makes sense then that the DC value of the RF pulse should be double that of the time bandwidth 4 pulse. Now typically in MR, we fix the duration, at least again on GE systems. The Philips system has a sophisticated way of optimizing the duration of the pulses sometimes in certain situations. But typically in MR what we do is that we fix the duration of the excitation pulse, and if we want a sharper slice, then we increase the time bandwidth product, right? If we want a sharper slice, we increase the time bandwidth product. And at the same time, what we do is we increase the gradient strength to compensate for the increased bandwidth of the pulse, right? So if we fix the duration and we increase the time bandwidth, if we fix t and increase bw, then we must have, or sorry, if we fix t and increase tbw, then we must have increased bw, right? And so to account for the fact that our pulse is going to excite spins across a wider frequency range, we have to increase the gradient so as to shrink that frequency range down back to the slice profile or slice thickness that we wanted in the first place. Okay, so here's an example of that. Let's say we have the following target slice profile here, right? And we can excite this with a time bandwidth 4 pulse, right? But now we want to sharpen up the profile but maintain the same slice thickness, right? So we are going to double the time bandwidth. This will give us the same width of the slice profile, but it will give us 1/2 the transition. Transition width, right? It'll be half as big as the left-hand side, and so we'll have gotten the sharper profile that we wanted. And at the same time, the amplitude of the pulse is going to be doubled. It's going to be 1 now, and the time bandwidth, the number of zeros in the pulse, is going to be 8, right? Okay. Now at the same time, though, this bandwidth here is going to be twice as large, right? Because we've doubled the time bandwidth of product of the pulse, but kept time the same. So bandwidth must have doubled. So really, this will be twice the frequency range, right? But what we're going to do is double the gradient amplitude at the same time, so that that frequency range maps to half the. So that frequency width. That frequency bandwidth maps to half the slice profile as before. Okay, so you can see here that I've depicted that we've got 2 times higher the gradient amplitude as on the left-hand side, and that would be necessary to get the same slice profile for this pulse as for this pulse if they have the same duration. Okay, last slide here. I wanted to give an example of calculating the gradient strength necessary to get a given slice thickness. So let's say that we have chosen a time bandwidth 8 slice selective RF pulse with a 2 millisecond duration. That's a convenient number, but it is actually fairly realistic. I believe on the GE systems the default excitation pulse duration is 3.2 milliseconds, but it can be 2 milliseconds. That's a very realistic duration. Now, if the slice thickness of the target slice is 1 centimeter, which is also fairly realistic, maybe a little thick, but pretty realistic, what is the gradient amplitude that we would need to play out simultaneously with the RF pulse, right, in order to get that slice thickness? Okay, so what we're given here is the time bandwidth and the slice thickness and the duration. Okay, so the time bandwidth is 8, right, and this is equal to the time, the duration of the pulse, which is 2 milliseconds, times the bandwidth of the pulse, which is unknown, right? But we can easily solve for the bandwidth, which would be 8 divided by 0.002, which is 4,000 or 4 kilohertz. Okay? So it's 4 kilohertz. Now the gradient has to be set so that this bandwidth of 4 kilohertz maps to a range of spatial locations between minus 1/2 centimeter to plus 1/2 centimeter, right? So a total slice thickness of 1 centimeter. And so that means that delta z, the slice thickness, will be equal to 1 centimeter. Okay, so we can use the following relationship. We can use the gradient strength times the slice thickness times the gyromagnetic ratio, right? So if you think about the units here, what do we have? We have centimeters, and we have Gauss per centimeter, and we have hertz for Gauss. So Gauss cancels, centimeters cancels, and we just get cycles. Right, or we just get hertz, and then that we can set equal to 4 kilohertz, right? Okay, so then that means that 4.257, which is gamma by 2 pi per Gauss, times the gradient strength in Gauss, That's 4.257 kilohertz per Gauss times the gradient strength in Gauss times the slice thickness, delta Z of 1 centimeter, must again be equal to 4 kilohertz. So what you can see here is that essentially a little over 4 kilohertz times 1 times G must be equal to 4, so that means G must be a little bit less than 4, or sorry, a little less than 1. So then G will be equal to, if you calculate this, you get 0.94 Gauss per centimeter. Okay, and that's it. So you should now be in a position to solve all the rest of the problems in the homework. Thanks.